Have you ever looked at a piece of work you've done? Um, Maybe it's an email you wrote or a presentation or some big project.
Oh, definitely.
Yeah, and you realize that by just, stripping away a few unnecessary parts, it suddenly becomes vastly more elegant and faster too.
Right? It's that incredibly satisfying feeling of editing. Less is more.
Exactly. Well, today we are taking a deep dive into that exact feeling, but we're looking at the fascinating intersection of performance optimization and human readability, specifically in computer programming.
Yes, and we're talking about a language called Haskell, which is really the perfect battleground for this kind of thing.
It really is. And our source for this deep dive is this very specific real-world artifact. It's a developer diary or blog post from May 27, 2026.
Right.
It's titled Optimizing Haskell via Function Composition and Partial Application. And it's actually part 146 of a series called Notes on Haskell Programming by an author we just know as Ang.
Yeah, Aang really breaks things down beautifully in this one.
So our mission today is to trace this single programmer's thought process through 4 distinct versions of the exact same line of code.
4 versions of one line.
Right. We want to uncover how a really routine refactoring task evolves from this clunky mechanical instruction into something that is just, well, mathematically beautiful.
And I think it's important to note, even if you listening right now aren't a programmer, the logical progression we're about to map out is incredibly satisfying to follow.
Oh, absolutely.
Because we're not just looking at the what of these code changes, we're really digging into the why behind them.
So to understand the end result, we have to start with Ang's initial problem.
Right, the baseline.
Ang is trying to write a function called iceText.
Yeah.
And the goal is to check if a chunk of data, specifically the first 124 bytes of a file, is text.
Yeah, and the standard way to do that is by looking for empty or null bytes, which are just zeros. If you find zeros, it's probably binary data, not text.
Exactly. So the original code logic goes like this. It converts those first 1,024 bytes into a strict byte string, right? And it stores that in an intermediate variable called chunk.
Right.
And then it checks that chunk with this logic. It says, not any equal to 0 in the chunk.
Which works. I mean, it gets the job done.
It does. But Ang's very first optimization is to just skip the conversion of those 10 or 24 bytes into a byte string before checking them.
Yeah, skipping that step entirely.
Okay, let's unpack this, because it eliminates the need for that intermediate variable, that chunk.
It does.
It's kind of like unpacking groceries. The old code is like taking an item out of the bag, putting it into a specific sorting basket, which is our chunk variable, and then checking the basket to see if the item is a vegetable.
Right, right.
But Ang's optimization is like, well, just peek directly into the grocery bag itself. You don't need the sorting basket.
I like that analogy. And what's fascinating here is that Ang points out removing this intermediate binding doesn't just make the code look simpler visually. It is explicitly tied to optimization.
Right, making it faster.
Exactly. Because by skipping that strict conversion step, the code actually does less unnecessary work. In Haskell, which uses lazy evaluation, forcing it to look at all 324 bytes at once and store them is just a waste of memory.
So the system can just look byte by byte, and if it finds a 0 right away, it just stops.
Spot on. It short circuits. It doesn't even bother with the rest of the bytes.
Okay, so now the code is leaner. It's more optimal.
Yep.
But as Ang looks at this new, faster code, which now reads not any equal to 0, and then takes the 10 or 24 bytes, a totally different kind of problem pops up.
And this isn't a machine problem anymore.
Exactly, it's a human one. Ang notes that the phrasing not any equal to 0 really impacts readability. Quote, it doesn't sound like normal English.
Right. It's a bit of a logical knot.
So the solution Ang comes up with is to rewrite the logic to all not equal to 0, basically meaning all of them are not 0.
Which is logically the exact same thing, just inverted.
Yeah. But I have to ask, so what does this all mean for the everyday programmer?
What do you mean?
Well, why does Ang care if it sounds like normal English, if the computer already understands it perfectly? I mean, isn't code supposed to be for machines?
That is a very fair point. And this raises an important question about who we are actually writing code for.
Right.
The reality is code is read by humans far more often than it's written by them.
Well, that's true.
Yeah, you spend hours debugging or maintaining a system. So that shift from it is not true that any of these are 0 to simply all of these are not zero, it removes this tiny bit of cognitive friction.
Because your brain has to do a little gymnastics to parse the double negative.
Exactly. You have to hold the negative in your head, evaluate the condition, and apply it. It's exhausting over hundreds of lines of code. So treating coding as a form of human communication, not just machine instruction, is huge.
I see. So it's about reducing fatigue for the next person who reads it,
Yeah.
which might even be you in 6 months.
Exactly.
Okay, so we now have code that is both optimized for the machine, because we dropped the basket, and readable as English for the human,
Yes, but we're not done.
right? Ang takes it one final step further, moving from this normal English into what's called idiomatic Haskell style.
And this is where it gets really fun.
So the final code transformation looks like this. It says, is text equals all not equal to 0.take 10024.
Notice anything missing there?
Yeah. The variable c, the thing actually representing our input data, has completely disappeared from the equation.
Vanish.
Ang calls this point-free or idiomatic Haskell style. It utilizes partial application and function composition, which is what that little dot represents.
Right, the composition dot.
Now, Ang breaks down the type signatures to explain why this actually works. Can you walk us through that?
Absolutely. So think of these functions as having specific shapes. The take function normally needs two things, a number, like 10 and 24, and the input data are byte string, and it spits out a resulting byte string.
Okay, makes sense.
And the all function needs a test are not equal to 0 check, and a byte string container to test. And it spits out a Boolean, like true or false.
Right.
But here, we only take the number. We don't give it the data yet. So it becomes a partially applied function. It's just sitting there, hungry for a byte string.
It's like a loaded spring.
Yes, a loaded spring.
Okay.
And the same for all. We give it the test, but no data. So it's another loaded spring waiting for a byte string so it can spit out a Boolean.
Okay, here's where it gets really interesting to me. I was thinking about this transitive flow.
Yeah.
It's exactly like an assembly line, where the conveyor belts are perfectly aligned.
Oh, I love that.
Right. You don't need a worker, which would be the variable c, to physically carry the item from machine A, the take machine, over to machine B, the all machine.
Because the belts line up.
Exactly. Machine A's output is a byte string, and machine B's input needs a byte string. They match perfectly. So you just bolt them together with function composition, which is that dot.
If we connect this to the bigger picture, it is just beautiful. When you look at Ang's type signature map, that middle step just perfectly cancels out.
Right.
It goes byte string to byte string, which then goes to a Boolean. So the middle byte string just becomes this invisible handoff.
It's completely seamless.
It is. It's pure logic. You're defining exactly what the pipeline does rather than micromanaging the actual data passing through it step by step.
Wow. So just to recap this incredible journey of a single line of code.
Let's do it.
First, we stripped away the intermediate variables, getting rid of that chunk,
Yeah.
to optimize for the machine's memory.
Yep. Dropping the sorting basket.
Second, we rewrote the double negatives, the not any into plain English, all not equal to 0, to optimize for human readability.
Saving our brains that cognitive friction.
And finally, we dropped the variables entirely through partial application and function composition to achieve this completely idiomatic, point-free elegance.
It's a massive evolution for just one line.
It really is. And, you know, for you listening, whether you're working on a complex spreadsheet or tweaking a recipe or editing a piece of writing, there is just this deep satisfaction in that iterative process.
Oh, absolutely.
Finding that perfect transitive flow where everything just snaps together seamlessly without any wasted effort, it's a great feeling.
It really is. And Ang actually signs off the post with this great little line. Rather intriguing, right?
I love that understatement.
Yeah, it's very humble. But it leaves us with this really fascinating paradox to think about. As Ang refined this code, it went from looking like clunky mechanical steps to reading like normal English to finally looking like pure abstract math without any variables at all.
Right, the data completely vanished.
Exactly. So the question is, does reaching that absolute peak of idiomatic elegance eventually loop back around to being intimidating?
Oh, that's a good point. If I'm a beginner, that point-free line might look like alien math.
Right. So where exactly is the perfect balance between highly readable human language and that flawless mathematical perfection? It's something every engineer has to wrestle with.
That is a phenomenal question to leave off on. Well, that wraps up our deep dive into the art of code optimization. Thanks for exploring it with us, and we'll catch you next time.